Hello, welcome to this third lecture about complete holomorphic vector fields and their singular points. My email is on the screen. Please feel free to contact me if you have any questions, doubts, complaints, and so on. So I will start this third lecture by telling you some things I told you about in the first two. I will start with a recap. And I told you that a holomorphic vector field on a complex manifold induces a holomorphic foliation away from the zeros of X. You have one-dimensional orbits like this one, L. And on each leaf, you have a vector field. You can restrict it. And on each leaf, you can have a translation structure. If you have a solution that's onto your leaf that is defined in some subset of C, a solution to your differential equation, then you can consider the inverse as a chart of this translation structure. Another way of saying this is saying that if you have an orbit of a differential equation like the ones we are considering, non-autonomous one, then locally time is well defined up to a translation, up to an addition of a constant. When you are in one orbit, you can definitely say what the time function is. Okay, so this is in general. This is what happens in general when you have holomorphic vector fields and complex manifolds. And I wanted to consider the holomorphic vector fields that do not have multi-valued solutions. And I told you about this notion by Palais and Rebello about semi-complete vector fields. So let me recall that a complete vector field, if you have a complete vector field, then each orbit is the quotient of C by a discrete subgroup. So these are the orbits of complete vector fields. So in a I talked about several equivalent ways of saying what a semi-complete vector field is. Let me just recall two of them. So the first one is that for each leaf, you can find some domain contained in the complex line and some Galois covering map, so onto your leaf, whose next transformations are translations. So it's similar to the first, to the complete vector fields, except that instead of taking the quotient of the whole complex line, you're just taking the quotient of some open subset. This is one of the definitions of being complete if this happens for every leaf. And the other condition, that is a nice one because it gives us an obstruction, is that, and I'll make a drawing again. So when you have one of your integral curves, you have your time form, the time that evaluated on the vector field takes the value 1. And if you take an open path, then gamma, then when you take the integral of your time form over gamma, this is always different from 0. This is another way of saying this. So your time, you have a locally well-defined time function, well-defined up to a translation. So if you give yourself a path, you can tell what the difference of the time in one point and the other is. And this condition is that the time you take to go from one point to a different one is always different from 0. Okay, so this is what the definitions, and we saw in the last talks, we talked mainly about local forms, local normal forms for semi-complete vector fields in dimensions 1 and 2, always under the hypothesis that the singularities were isolated. And today I would like to talk about what happens when your singularities, before that, so we just saw the definitions of complete and semi-complete vector fields. So with the first definition, you clearly see that complete vector fields are semi-complete. That the restriction of a semi-complete vector field to an open subspace to an open subset of your ambient manifold is still semi-complete. You take the orbits and you shrink them. You take just subsets of these orbits. They will all still be quotients of some domains in C by some group of translations. This shrinking makes it possible to speak about germs of semi-complete vector fields, and that is what we did last time. And the the main motivation is that germs of semi-complete vector fields will give you local models for complete vector fields. Okay, so this is more or less what we did, and we talked about some normal forms for complete vector fields, always under the hypothesis that we have an isolated singularity. And today we will talk about non-isolated singularities and what happens and how do you cope. And how do you cope with these non-isolated singularities? Okay, so let me start. So we are considering vector fields and not just foliations. So this, I know this school is about foliations. So in general, when you have a vector field X, like the one we're seeing here, you can write that, you can factorize it into two parts. One part, vector field, whose coefficients, so we are in surfaces. I will work in surfaces for the rest of this lecture and the following one. So I will be in surfaces. So you can write your vector field and you can write it as a product of two elements. One of them is a vector field such that the coefficients do not have any common factor up to units, A, B, relatively prime, and then one part F where you have all the zeros of the vector field. So A and B do not have common factors, so the singularities of A and B, the singularities of the vector field here, are isolated. And F gives you zeros of the vector field if F is not a unit. F gives you zeros as a curve of singularities. And this will be the source for non-isolated singularities. Okay, so this F and this the F, the function, and the foliation, and the other part are only defined up to units. You can say that the foliation is given by this vector field, and the other one gives you the curve of singularities. Okay, so there are many interesting things that happen with non-isolated singularities. And there are two kinds of curves of singularities. And let me just take a point at generic point of the curve of singularities. And then two things can happen. So either your curve of singularities is transverse to the foliation, or it is tangent to the foliation. Here in the drawing, we know it's tangent to the foliation. These are the two things that can happen. So in the first case, in the case where you have, if your curve of singularities is transverse to the foliation, then you know that if you restrict your vector field to one of these integral curves, what you will see will be something like up to a factor, still something like x to the n e over the x, if your if n is a multiplicity of your curve of singularities. And this falls within the scope of what we saw yesterday, vector fields in one dimension. So from this, you can say, for example, that n is at most 2, and you can say more things about it. So this is, in some sense, a parameterized version of what we saw last time. And it is this part, the second part, that will be a more interesting one, the case where the curve of singularities are invariant by the foliation. Okay, so in order to tell you, so the idea is that we will try to make sense. So here, what happens is, so the vector field here, this purple invariant line, is 0. So if your vector field goes with some speed here, it will go slower as the vector field will be smaller and smaller as we approach the singularity. We do not have, and in the singularity, in this curve, the solutions will be stationary ones. So these are zeros. The solution is just map the whole complex line onto these points. But we will try to make some sense, to give some geometry to these curves. Okay, so before I do that, let me recall you what an affine structure in a complex curve is. We have the affine group. here the group of affine transformations of the complex line. It contains a group of translations, and it also contains Euclidean geometry when we consider affine maps with linear part of module 1. And let me tell you 3 equivalent ways of defining an affine structure on a curve L. So the first one is just take an atlas for your curve L, take coordinates within the affine line. So atlas for L in C with changes of coordinates in the affine group. That's one definition of what an affine structure on a curve is. The other one is they will all be equivalent. The other one is take a cover of your curve, and in each element of the cover define some vector field xi in your open set ui, and then just the condition that when you overlap, when you have 2 overlapping open sets, the condition is that you should have a constant that goes from one vector field to the other. That also gives you an affine structure. And another possible definition of what an affine structure on a curve is consider in the universal covering of your curve a vector field, and such that the deck transformations act by multiplying your vector field by a constant factor. So if you take any of these definitions, you get an affine structure on a curve. And we already saw examples of translation structure of affine structure on curves that are translation structures. So you can think, instead of thinking on the geometry induced by a vector field in a curve as a translation structure, you can also think about it as an affine structure. Okay, so these are affine structures on curves. We have already seen some examples. And the idea is that what I told you before, when I will make the same drawing, when I have a curve of singularities that is invariant by the foliation, and I'm here doing the same drawing I had before. When I have this situation, well, then if I have this, then in local coordinates, I can see that I can write my vector field in this way, just a vector field up to some x to the n will be, this n will be the order of the multiplicity of the curve of singularities, and h one factor. And what I claim is that although the limit translation structure does not make sense when I get to the purple curve, what I claim is that the affine structure, the limit affine structure, does make sense. Okay, so I claim that I have an asymptotic affine structure in the purple line that is well defined, it is uniquely defined. So the statement is that if I consider, instead of the Euclidean, instead of the translation structures, if I consider the affine classes of these translation structures on the leaves of this vector field, then they extend to x equals 0 to the purple line in a unique way. Okay, so there's a well-defined affine structures. So let me give you the proof of this fact. So this vector field x has as first integrals all the functions of x. Okay, now if I multiply my vector field x, or any vector field, if I multiply it by a first integral, then I will not change. I will change the translation structures along the leaves, but I will not change the underlying affine structure. If I have one vector field or twice the vector field, I have, from the affine point of view, the same structure. So if I consider my original vector field, but I multiply it by some function of x, then I will not change the affine structure along the leaf. And if I do this in a way such that this vector field does not vanish at x equals 0, then I will have that, okay, so this function should be essentially removed. So I will consider meromorphic and holomorphic vector fields. This doesn't change anything. So I can choose one first integral such that when I multiply the first integral by, when I multiply the vector field by this first integral, I get a non-vanishing vector field on x equals 0 in this way. By the way, in this slide, I am supposing that, in fact, this factor h is equal to 1. You can suppose this out of a change of coordinates. And then all these vector fields, all these vector, so I chose first integral, but all the different first integral, all the different vector fields in the limit that I can get to when I change my first integral differ by a constant. So there's a well-defined affine structure. Okay, so there's some geometry, some limit geometry when I reach these curves, in these curves of zeros that are invariant under the vector field. Okay, so the thing is that, so this is in general, so there's no semi-completeness hypothesis here. This always happens. And the thing is that in the semi-complete case, this limit structure, we have this limit affine structure, we have a property that's similar to semi-completeness. So let me define what a uniformizable affine structure with singularity, affine structure is in a curve. Okay, so consider L, a curve with an affine structure. And I will say that the affine structure is uniformizable if it satisfies one of the following two properties. They are equivalent. The first one is that L as a curve with an affine structure is a quotient of a domain, of an open subset of C under some group of affine transformations. See, this is exactly this is very similar to the condition we had for a semi-complete vector field. In a semi-complete vector field, we have that your curve is a quotient, your orbit is a quotient of an open subset of C under a group of translations. Here I'm saying that an affine structure is uniformizable if L is a quotient for a domain of C, now under a group of affine transformations. This is the first condition. The second condition is an equivalent one. The second condition is that when you consider your curve, and you consider in your curve a path, gamma. Okay, now, what I can do is I can develop the affine structure on this curve along this curve gamma. And the condition for uniformizability is that when I have an open path, I need the developing, let me just put here, so this will be the developing. So this takes values in C, and what I want, the condition for the definition, one possible definition for uniformizability is that this open path maps to an open path. Okay, maps. So the development of the affine structure along gamma maps the endpoints of the path to different points. Okay, so in the case of when I have a vector field, the developing of this translation structure will be just the integration of my time form. So this is exactly the same condition. So I will not show you that these conditions are equivalent, but I will just show you that the first one implies the second one. And again, the second one will be interesting because it will give us a way to calculate obstructions. So suppose we have the first condition that this curve here that I have to the right, this curve L, is a quotient of some domain here. So again, this is the same drawings we did in the first session. So suppose we have, maybe there are some punctures, I don't know, but suppose we have some domain omega that covers my curve L, okay? And such that the group of deck transformations is an affine one, okay? And so in this case, I can, on the one hand, lift my path, gamma tilde, but this lift is at the same time the development of the affine structure along gamma. Okay, so if the development of the affine structure along gamma, equivalently, if the lift of gamma gives me a closed curve, if I start with an open curve and I lift it, and I suppose that it maps the endpoints to the same points, I reach a contradiction because this map is a covering map. This arrow is a covering map, and if this curve is closed, then gamma should be a closed curve. But the hypothesis is that it is an open curve. Okay, so this shows that the first condition implies the second one, and the second one is useful because it can be used to calculate obstructions to uniformizability. Okay, so this is what uniformizable affine structures are, and I still have to link it with semi-complete vector fields. And the thing is the following: if I have a semi-complete vector field on my complex manifold M, and I have C, the component of the curve of zeros that is invariant by the foliation, then the affine structure on C is uniformizable. Okay, so the affine structure, if I have a semi-complete vector field and I have a curve of zeros invariant by the foliation, then this curve inherits this very particular kind of affine structures. Okay, so let me give you a proof of this fact. So let me give you now this will be a purple curve. So this is a curve of zeros. And this one is invariant by the foliation. And let me, in blue, paint one of the other curves we were considering, one where we do have a definite vector field. Okay, so within the curve of zeros, let me draw one curve gamma, an open path, and I will suppose that this curve of zeros does not have a uniformizable affine structure, and I will suppose that I have a curve gamma, which has different endpoints, an open curve, and I will suppose that under the developing of the map, under the development of the affine structure, these endpoints get mapped to one point. Okay, so I have this curve gamma. And I did a similar argument last time when I proved that the space of vector fields is a closed one. I gave some arguments. So in this case, the same thing happens. I can lift my curve gamma to a curve gamma tilde in a neighboring curve, and I can do this geometrically. I can do this in a way that locally I have an isomorphism of these two affine structures, because of course the affine structures will vary holomorphically, in particular continuously. And I could, as I do this lift, this geometric lift of my curve gamma, I will also have a curve gamma in my curve, which will have the same property that the development of the affine structure along this curve will be the development of the affine structure along this curve will have closed endpoints. So this is gamma tilde. And what I have, so this thing means that when I have the integral of this time form along L prime, along this gamma prime, this condition implies that this is equal to 0. Okay, because I would have the same property. And since I took one L prime that was sufficiently close to L, then of course this curve gamma tilde will be open as in the image. So this would imply that the vector field on L prime is not semi-complete because the development of the affine structure along L prime is just given by the integration of the time form. Okay, so this will be very useful. I have a semi-complete vector field on a manifold, and I see a curve of zeros that is invariant by the foliation. I can read in this curve. I can see if there's something in this curve. I can read obstructions for semi-completeness in this curve, and these things that we can, these obstructions in general, we can calculate them. Okay, so let me give you some examples. Last time we saw these examples of quadratic homogeneous vector fields that appeared in the statement by Rebello and Gis about germs of complete vector fields with isolated singularities in C2. So all these vector fields that appear in the screen are semi-complete vector fields. And for example, the last three look more or less in this way. So we have three separatrices that pass through singular points. You see clearly x equals 0 is one, y equals 0 is another one, and there's a third one because we have a quadratic vector field. And when you blow up, you will find an exceptional divisor, and you will find these three separatrices here. And the thing is that you will find along the exceptional divisor, you will find a curve of zeros. It will be invariant by the foliation, but it will definitely have a curve of zeros. So this is exactly in the setting that we were talking about. So there's one limit. All these vector fields have some definite limit affine geometry along this divisor. And these affine geometry is one that we can obtain by a quotient of some domain of C. Okay, so I will come back to this later, but this is one setting when these affine structures appear. Okay, so this is one example. So consider I'm here in the complex plane C, and I consider one subgroup of the affine group, which is the group of, I pick a triangle here, and I can consider the group of Euclidean transformations generated by the reflections along the sides of this triangle, and then I can consider the index 2 subgroup consisting of orientation preserving transformations, and this is of course a subgroup of the affine group. And when I look at the group that acts on C, I see that it has as a fundamental domain the union of one triangle and its image, and then it glues together by identifying the sides. So when I glue this together, this will give me a sphere, and this sphere will have three special points coming from these vertices. So I will get in the quotient, since I am acting by Euclidean transformation, in particular affine transformations, I will obtain, and I'm taking the quotient, so if I remove just all the vertices, I will find three punctured sphere with an affine structure that will, and this affine structure will be by construction a uniformizable affine structure. And it turns out that this affine structure is exactly the one that you will see along the exceptional divisor of these vector fields. Or another one. Okay, so one of these vector fields we have this affine structure. So let me just tell you. So I will go in a while, in a minute, I will go I will start discussing some semi-complete vector fields in the quotient of birational geometry. And we will see these sort of things appear many, many times. We will see compact curves such that in the complement of some points, like these ones, we will have an affine structure well defined, and this affine structure will be uniformizable in this case. So I can tell you what sort of curves we will find and what sort of affine structures we will have on them. So this setting is, so we have a compact curve, and we will have on this compact curve some points. This will be the singularities I will be talking about. So these are smooth curves, and I will have some finite number of points, and I want to have a uniformizable affine structure in the complement of these points. So that these are the only possibilities. The first ones are, of course, elliptic curves. So these are C not a lattice. But so these come in many flavors. This lattices can be deformed, and some of these have. So these are uniformizable by construction. These are the quotients of C under some group of translations, and they have quotients like the previous one I showed you. So you will find these quotients will be, you have some quotients will have 3 orbifold points, and they will be related to elliptic curves with multiplication, with some point fixing automorphism, and they will be related to some of the 3 special triangles that tessellate the plane, the equilateral triangle, the half equilateral triangle, and the one we saw that has 1 right angle and two other ones. And of course, in this quotient, I will also find the quotient by the hyperelliptic involution. So this will be related to just some triangles. Okay, so these are also uniformizable affine structures. If you take an elliptic curve and you take the quotient by its elliptic involution, you will find a sphere with 4 special points, and in the complement of these points, you will find an affine structure, and this will be a uniformizable one. So these are these examples. The other source of examples will be take P1. So the point at infinity, there you do not have a well-defined affine structure, but in the rest of it, you will find one. And then just take the quotient by, so this is 0. Here I do have a well-defined affine structure. I just take the quotient by a finite order automorphism. So this is realized by the map Z to the N. So here I have a group acting, and the action is by affine transformations. And so in this quotient P1, I will also have a uniformizable affine structure. I will find 2 special points, one coming from infinity and one coming from 0. I will no longer have an affine structure in 0, but I will find an affine structure. Here we have other ones. So these are P1 and its quotients. We have well-defined affine structures there coming from the affine structure in the complement of the point at infinity in P1. We have other ones, say P1 with this vector field. So this is I have P1 and I have the vector field d over dz. And I told you that in the complement I have a complete vector field. So in particular, it gives you the complement of this point, well-defined affine structure. There will be in P1, this will be a singular point of the affine structure. And I will find another singular point of the affine structure at infinity. You can take a quotient of this one. If I take this involution, this will exchange the point 0 and the point at infinity, and this will multiply the vector field by -1. when you do this. So the quotient, you do not have a vector field, but you do have a well-defined affine structure. And finally, you will find elliptic curves. Say if I take C and I remove 0, and I take the quotient, say, by the map that multiplies Z by 1/2, and I take the quotient and I take fundamental domain, in the quotient I will find an elliptic curve with a different affine, with an affine structure. This affine structure will also be uniformizable because it will be obtained as a quotient of an open subset of C by a group of affine transformations, but it will be different from the first ones. And this is it. This is all the list you have. So, for example, so all these curves will be elliptic or rational. So, for example, if you see a vector field and you see a curve of zeros that is invariant by your vector field, and for example, it has genus 2, then for sure your vector field will not be semi-complete. If it has higher genus, of course, it will not happen as well. It has to be rational or elliptic, and the geometry should be one of these geometries, because this is all there is, as long as you have compact curves invariant. So this is a this will give us a very strong restrictions for vector fields to be semi-complete, a restriction and also an obstruction for these vector fields to be semi-complete. Okay, so I think this is a good place to stop. We will continue in the next lecture with the birational point of view. I will see you then in the next lecture.